Okay, good morning and welcome back. Today we will talk about synchrotron radiation. Synchrotron as a light source. We will give you an example how to generate synchrotron radiation and how to use this light source to study the physics. Okay, you can sit back and relax because this part and the previous class was not included for the final exam, just for your reference only. You can study a synchrotron radiation from different cores. The synchrotron emits intense radiation with a very broad frequency spectrum in a beam of extremely small angular spread 1 over gamma. It's a unique research tool, unique, and can also be used for microfabrication. I will give you a paper talk about how to use X-ray microfabrication technique that called LIGA to fabricate component, very small components and other applications. So from this viewpoint, I am the user of X-ray, and I am also familiar with synchrotron radiation because I am. I will show you little by little. The photo below shows the light source facility at the National Synchrotron Radiation Research Center in Taiwan. We have a booster synchrotron and we have a storage ring inside. Oh, next page. Okay, electron bonds are first accelerated to an energy of 1.5 GeV in a booster synchrotron and then sent to the storage ring as a synchrotron. That's the booster synchrotron RF system to accelerate the particle, where the energy is maintained at 1.5 GeV while the electron provides synchrotron radiation to users around the ring. I remember this one is much higher, 3.3 or something, while the electron provided to the user around the ring. The electrons are powered by the microwave from the RF systems, powered by the microwave and radiate due to the magnet. Okay, that's the new synchrotron radiation facility. Taiwan photon source, Taiwan light source. Okay, this is Taiwan photon source, and the old is Taiwan light source. So the photo I just give you is the old source, old synchrotron. That is Taiwan light source, Taiwan light source booster ring, Taiwan light source storage ring. And here we have a new synchrotron radiations, Taiwan photon source storage ring. It's much larger, much larger. Where is Tsinghua University? Any idea? Here. Tsinghua University is here. Okay. Okay, move on. Okay, that's the new Taiwan photon source. The old is 1.5, but new is 3.3 GeV, and current is 400 milliamp. And we have other uh, other specifications here. Okay, RF power 720 kilovolt to accelerate particles, and RF maximum voltage 6.5 megavolt. And the building, the diameter is much larger, 223 outer diameter, and inner diameter is also much larger, 400, uh, inner diameter 139. Okay, so it's quite different from the old. Okay, so the acceleration, we need a microwave, 500 megahertz microwave. So how to couple the energy to this cavity? We use coupling structures. So this is TM010 modes. A bunch of electrons move inside, and it will accelerate or decelerate or doesn't affect because depends on the phase. So we need to synchronize the phase to make sure the wave can accelerate the particle. Okay, so this cavity is the old cavity called Doris cavity. Right now, they use another cavity called uh, superconducting cavities. Okay, they use in the old time they use 60 kilowatt klystron, and klystron is electron beam, and they can generate microwave 500 megahertz. Now they switch to another source, solid state device, and they use many solid state device. Each one provide 1 kilowatt, for example, and combine 60 or 100 to give 160 kilowatt. That works well. Therefore, I cooperate with them. They develop 500 megahertz microwave, and we develop 915 megahertz. Okay, 915 for material processing. Okay, and we also study the cavity, the Doris cavity with them, our lab. Okay, that's the photo of National Synchrotron Radiation Research Center booster synchrotron shows. This photo showing some key components of the accelerator. So here is a coaxial transmission line. It just transmit the microwave to the cavity. And we have acceleration cavities. We have some tuner. We have a pumping station to pump the vacuum to a very high value. That's for electron beam tunnel in high vacuum. And we have a dipole magnet, quadrupole magnet, uh, yeah, octupole magnet, something like that. Okay, accelerate, decelerate, accelerate the particle, decelerate the particle, extract the energy. Okay, so we have collaboration with them. We use high vacuum pump. We need a magnet, therefore we cooperate. We need a 6 Tesla to 8 Tesla superconducting magnet, therefore we cooperate with them. Okay, that's the beam line. One beam line, another beam line, another beam line. Each beam line means related to here, a bending magnet. Okay, and in this beam line, we can use beam line to study many physics, to X-ray, to study the material behavior at X-ray, to use X-ray to fabricate some device. So very useful. Okay, finally, I will give you 4th slide, I will tell you how to increase the energy of the source. How to increase. We have two ideas. One is undulator, the other is wiggler. I just show you when we bend, we use the magnet, dipole magnet, bend, it will radiate. But the radiate is sometimes still not good enough, not strong enough. Therefore, we use another structures that is undulator, periodical structure, and wigglers to enhance the radiation source, to enhance the radiation. The broad spectrum of radiation emitted by the relativistic electrons bent by the magnetic fields of synchrotron storage rings provide a useful source of energetic photons. As application grew, the need for brighter sources with the radiation more concentrated in the frequency led to the magnetic insertion device 插件元件 that called wigglers or undulator to be replaced by the synchrotron ring. The magnetic properties of these devices cause the electrons to undergo spatial motions, not simple motion, but spatial motion that results in the concentration of the radiation into a much more monochromatic spectrum or a series of separate peaks. Enhance the intensity, increase the brightness. Okay, that's the purpose. The essential idea of undulator and wiggler. The essential idea of undulator and wiggler is that the same. That means the essential idea is the same. That is a charged particle, usually an electrons, and usually moving relativistically is caused to move transversely to its general forward motion by magnetic field that alternate periodically. That is, the particle will bend up and down, up and down. Sorry, it's not up and down. That's x direction, that's y directions. And the south pole, south pole, that's magnet. We have a lot of magnet. And this magnet will change the motion of the particle. So it's not move in up and down, up and down. It's like left and right, left, right, left, right, left. Okay. And you know, the particle, the radiation will be emitted in these directions. With this one, they will enhance, they will strengthen the brightness, enlarge the brightness. The external magnetic fields induce small transverse oscillations in the motion. The associated acceleration causes radiation to be emitted. So that's the angle, the particle motion. Okay, so what's the difference between undulator and a wiggler? Wiggler means the phi is very large. Phi is very large. What is phi? Phi 0 is here. That's very large. And much greater than delta theta. An observer detects a series of flicks of the searchlight. That is, this kind of motion is very large. So delta theta is angular width of the radiation about the path. On the other hand, undulator is better. the angle is small. The searchlight beam of radiation move negligibly compared to its own angular width. The radiation detected by the observer is an almost coherent superposition. Therefore, for undulator, the intensity will be higher. The brightness will be higher. The contribution from all of the oscillation of the trajectory, that depends on what you want. So if we have a bending magnet, that's the energy that corresponds to frequency, and the brightness is here. But if you have wiggler, the brightness increase a little bit. Bending magnet, just one bend, okay? Wiggler, doing, 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 okay? Undulator, doing, 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 doing. Therefore, intensity for the undulator is much, much higher. Much, much higher. So it depends on what you want. Depends on what you want. Depends on your applications. Finally, let me show you the highest particle speed of Large Electron-Positron Collider, LEP collider. The Large Electron-Positron Collider, LEP, is one of the largest particle accelerators ever constructed. The LEP collider energy eventually topped at 209 GeV with a Lorentz factor gamma over 0.2 million, 200,000. LEP still holds the particle accelerator speed record. So gamma for such a large, so 1, you need 1 divided is about this value. And beta is about this one. Very, very high. Very, very close to 1. Very, very close to 1. So just millimeters per second slower than the speed of light. But anyway, matter cannot exceed the speed of light in vacuum. That's impossible. Matter cannot exceed. But wave, yeah, we have a chance. Yeah, wave can exceed the speed of light. Okay. Okay, this the homework just 3, not too much, because synchrotron radiation is quite difficult. So I do not ask you to, I do not give you too much problems. You should study the lecture note carefully. The final exam will be open book. You can you can write everything on your lecture notes. All your knowledge on your lecture notes. It will be open lecture note only. Okay, keep this in mind. We will have a test at our classroom, and it is open book. The only book you can open is the lecture note. So please write your answer in the lecture notes. All your information in the lecture notes. The last 2 class is quite short because just give you, it provides the information. So it can be really short. Okay, that's the end of this semester. Bye bye and see you next time.